Another problem today, determine the ion values and frequency for the stepped bar as shown. Commonly, it is being asked in university for to solve frequency problems. Got it. Now, Young's modulus is given and densities are given. Okay, so we'll proceed further. Now, if you see, this is the problem statement. As I told earlier, whenever you are solving any problem, just a second. Whenever you are solving this problem at undergraduate level, try to divide the problem into smaller number of elements. So generally it is we take two elements. So if you are taking two elements, you will have 3 cross 3 matrices. Got it? If you keep on increasing the number of element, your matrices will increase and complexity will increase. Got it? So that's why we kept it for two elements. Now these are all the parameters given, and if you see here, these all terms are self-explanatory in nature. The corner points are called nodes. Nodes, there is two standard definitions. First is where known field variables are applied. Field variables like temperature, velocity, etc. And those are applied to know unknown field variables. Now, for example, you will apply some boundary condition here to know what will the condition at this spot. Got it? This is one standard definition. Another is where degree of freedom are defined, but this is valid only for two dimensional. Got it? Anyway, so these all are parameters given. Next, what we will do now, this is for element 1, it is given, and this is for element 2. So all the things are given. Now what we are going to do now is this has been done. So all things are given. So when you divide into element 1, element 2, what all the parameters are there, so you need to deal with that. Now this is the fundamental element equation which you need to understand. Okay, so K is what? Global stiffness matrix. So now what you have to do, you have to formulate a matrix. Got it? You have to formulate a matrix for the single element, and then when you add it, so it becomes global stiffness matrix. So in university it will be asked, okay, what is the difference between matrix and global stiffness matrix? Global means you're adding the element. Okay, after adding you get whatever overall assembly of the matrix. So this we will try to solve this problem. Now so what we have done, we consider element 1. So this is our element 1 for stiffness matrix. This is a same, the stiffness matrix is same for everything. So just extra term is a mass matrix here. So you have to remember the formula. So K1 is equal to A1 E1 by L1 whole bracket 1 minus 1. So this you have to remember, and we have just substituted the value for element stiffness matrix. Similarly, we will substitute for mass matrix. Okay, so got it. So for element 1 we have calculated. Similarly we will do for element 2. Got it? So this becomes our element 2. Everything is same, only one thing is you have changed the values. Got it? K1 K2 what we have got. Okay, so we got individual stiffness matrix for element 1, we got individual mass matrix. Got it? So so once we got that, so now we will do, we will add it. Got it? So now this is very crucial, which you have to see here. See, this is my element 1. Got it? So element 1 neighbors or element 1 nodes are 1 and 2. The corner are nodes. Got it? So element 1 is not sharing anything with our node 3. Got it? That's why your 3 are 0 here. Okay, similarly when you are going for element 2, element 2 has only corner points at 2 and 3. Got it? So it will not have any of the one part. That's why this has been kept 0. Got it? Now this is element stiffness matrix we got for each individual element. Now if you want for the whole system, then we have to add it. So that part is called global stiffness matrix. Okay, now before we jump, we will calculate the mass matrix also. So this is the mass matrix which we have to remember. I think I have not used some, just a second, minus is not there. Okay, we will see later. Some error I think is there in this plus minus sign, a typing mistake. Okay, not an issue. You can check back and do that. So same like this element 1 is there. So element 1 is there, so there won't be any anything at the third node. Similarly, there won't be any uh, this element 2 is not sharing a single node with 1, so this becomes 0. Now we will add these two matrices. Got it? So when you're adding, if you see node 2, node 2 is being, where is that? Yeah, node 2 is being shared by both the elements. So here in the middle it is being added. So here everyone get confused why it is being added twice. The reason is node 2 is being shared by both of them. Similarly, so mass matrix also we will see. Okay, so element matrix we have seen. So this is mass matrix. So if you see here also in the mass matrix, yeah, there was a mistake here, minus in the previous, so there won't be any minus. Okay, so if you see in mass matrix also, these at element 2 it is being added. So now we will substitute all the values in the equation. So this was our fundamental equation, K minus omega square into mass matrix. So K is global stiffness matrix, M is mass stiffness matrix. So we will substitute all the values. So K1, K2 you can put the value A2, E2 by L2. Got it? So if you substitute these all values, you will come to know. Got it? So just a second, yeah. So mass M1, M2 is equal to this much. So these are self-explanatory in nature. You need to put the value, you will get the results. There might be, see, some typing error or calculation mistakes. There might be there. I generally see that. Got it? But that you can rectify by yourself. But you need to understand the concept. That's it. So this is the matrix. No, so we have written what I have done here. 13 to 10 to the power 10. If you see in the previous, 13 to 10 to the power 10 is being common, and 8500 is taken as common in from here. So our final resultant matrix will be like this, which we have successfully obtained here. Got it? K minus m omega square into is equal to, it is equated to 0. For eigenvalue problems, we equate it to 0 to get the desired result. Now what we will do, we will divide it by 13 to 10 to the power 10. So once we have divided it into 13 to 10 to the power 10, so we will get this resultant matrix. Now this we are doing to have a more simplified version. So FEA is actually approximate method to solve a physical problem. Okay, now what we have done, we considered here this, just a second, I think I missed something. No, it's okay. Okay, so lambda is equal to 1.18 into 10 to the power minus 7. So we consider lambda is equal to, so actually this should omega square I have missed, I think. Anyway, it will be next slide. So we considered it. So how will the operation, this will be subtracted from this, this will be subtract or added by this will be added by this. Similarly goes for, so this will have an operation with this part, this will an operation with this part, this will an operation with this part. So it's self-explanatory in nature. So hope this justify the statement we have done till here. Now if you see here, the step bar which we took at the first is fixed at node 1. So node 1 all terms will be cancelled. So once the node 1 all terms are cancelled, we are left with only these terms. Got it? We are left with only these terms. So these terms we have written here properly. Now it is reduced to a quadratic equation. So this is how generally in maths also we solve the eigenvalue problems. So we have successfully done till here. So it is solved to a quadratic problem, and so we got lambda here. So we got two values of lambda. Yeah, that's what I earlier I missed omega square. So lambda is equal to this much into omega square. So omega 1 by omega 2, we successfully got it. So this is how we got eigenvalue and frequency, first two frequency.